take you to the practice quiz. And I'm back from seeing my mother in Michigan, and she had a kind of a resurgence, and was doing, okay and communicating to us, but she'll be leaving this world quite soon. She can't. She's got a broken arm and a broken collarbone, and so she can't move, and she can barely whisper loud enough to be heard. And we're just making her comfortable. All right. So number 1, how many points on a line? And then 3 to the negative 2. Okay, 30 seconds. Alright, so this first one, how many points on a line? We tend to think of lines not necessarily as points, but you can think of them as a whole bunch of points placed together. And they just happen to all line up on a line. And if you think of it like that, it's an infinite number of points. And this perspective of a line that is really just a whole bunch of points that happen to line up together is what we're going to be using later on today in the new section. Okay, and 3 to the negative 2. If exponents is repeated multiplication, we can think of this as repeated division. This 1 is now being divided by 3 twice, and it's 1/9. Okay, and alright, a little bit of feedback on numbers 1 and 2. And you can go ahead and enter that feedback as soon as you type it in. Okay, and let's go to number 3. X plus 3 in parentheses squared. And 30 seconds more on number 3. Okay, and my first instinct on this one is to write x squared plus 9, distribute the exponent. But if there's more than one term in the parentheses, that's wrong. It's instead got to be this. Anything squared is times itself. That's what it means. And then when I do this, I'm going to do it this way. 3x and another 3x. That gives me 6x plus 9. Okay, and a little feedback on number 3. Number 4. Thirty seconds. Okay, we don't know what x is, but it's very common that we don't give answers with negative exponents. Most people are more comfortable with positive. This means the same thing as x to the third over 1, or just x to the third. And that's it. It moves to the other side of the fraction bar. We saw this one move down and then become a positive exponent. This one moves up and becomes a positive exponent. A little feedback on number 4. Number 5, go ahead and do that. Thirty seconds more. Okay, now do number 6. Thirty seconds more. Okay, so 5 and 6 look a lot alike, but they act totally different. Because we think of what's in parentheses as one item. Here, the two items are added together, two separate terms. Here, they're multiplied, all one term. So it's incredibly different. And this one is, the parentheses don't do anything. You just drop them, add the like terms. 5m minus 1. Here we gotta, I'm going to do this shortcut method. And then I can do it all in my head. 6m squared, the two middle terms is minus 4m. Last one, minus 2. Okay, a little feedback on numbers 5 and 6. Okay, it's kind of a 50-50 split. Helpful review, not needed, so at least some needed. Okay. And number 7. Okay, 30 seconds more. If you don't finish all the way, that's fine. You can at least kind of see if your process was right. All right, now, number 7 is not really like either number 5 nor number 6, because these have addition and subtractions inside the parentheses. But it's much more like problem number 6 than it is like number 5, where that's all one term and that's two separate terms and you're adding like terms. This is all one term altogether. There's not a single addition or subtraction. We call this a monomial. When it's all one term, when we start to look at it in terms of, you know, is there plus signs or multiplication signs between the parentheses, we kind of see that all we're going to do is rearrange. We're going to put all the numbers, the x's, the y's, and then the z's, and then I'm going to put these numbers kind of with the appropriate, so the y, the a, and the z right underneath these other z's. Okay, so we can kind of think of it as 4 separate problems: the number problem, the x problem, the y problem, and the z problem. And now, first of all, I'm going to handle negative divided by negative, makes the whole thing positive. So my whole fraction is going to be positive, and this plus sign is unnecessary, but just remind me of that's what's happening. And then divide this by 5, divide this by 5, oops, 5, and I get 2. And I'm going to have 4 on the top. And then with the x's, I'm going to get 7 x's, and then 2 of them are going to go away. They're going to cancel out. So there's going to be 5 x's. And then I'll look at the y's. I'll have 4 of them on the top, expand that out at the bottom, y, you know, 8 y's. And there'll be 4 extra y's on the bottom when I cancel them out. It'll be y to the 4th over y to the 8th. And then the z's, you could just kind of think, well, this one z and this one z cancel out. And I'm left with this z squared up here. This is all I'd really need. Give me a little feedback on number 7. Oh, maybe on the wrong side of the fraction, Randolph. Some on the top, they're supposed to be on the bottom. Yeah, that can focus on that. Write that number in scientific notation. Thirty seconds more. Okay, so the number is going to become always a number between 1 and 10. So the decimal point goes just to the right of the first non-zero digit. 7.8 times 10, and then it's either going to be a positive or a negative exponent up here. I always try positive first, see if it seems reasonable, and then if not, I change it to negative. Now, if I multiplied this by 10 to the first, it would move it to the right one place. Well, how many places do I have to move it so the decimal would become over here? Well, I have to move it from here 2 places, and then 3 more is 5, 3 more is 8. 7.8 times 10 to the 8th. And then I check, did I put the right sign on that? Was it supposed to be positive? Yeah, when you multiply 7.8 times 10 to the positive 8, it makes it bigger, it makes it look like that. Okay, now do number 9. Put that number in scientific notation. Okay, 15 seconds more. Alright, so this one, we got to move that decimal point, so it's just to the right, the first non-zero number. And then I figure out how many places I have to move it. I had to move it 3 places and then 1 more, 4 places. And I might start by putting it as a positive 4 and then say, does that make sense? Well, no. If I multiply 4.127 times 10 to the 4th, it makes it bigger, and I have to make it smaller. So you divide by 10 4 times, and that moves the decimal place to the left 4 times, and that's correct. Alright, so give me a little feedback on numbers 8 and 9, please. Okay, Jacqueline writes, still confused on why the y goes to the bottom. Let's look at that. Let's come back here to the previous. Alright. If there's, in the top, these two y's gathered together and became y to the 4th. Y cubed times y is y to the 4th. But there's more y's on the bottom, so we visualize 4 y's up there and 8 y's down here, and then we're going to be dividing or canceling them out. Divide by all these y's, and then all the y's are left. If there's more y's in the bottom, they got to end up down here. So Jacqueline, you weren't the only one. Randolph was talking about getting them on the right side of the fraction as well. Hopefully that clears it up a bit. Let me look back.
It did, thank you.
You're welcome. Alright, this is the last one. Let's practice Gustav. Go ahead. Okay, 30 seconds more. Okay, so what this is you got to get rid of the parentheses. And the only way you can get rid of the parentheses is by using the distributive property. We're used to seeing something out in front of this parenthesis, but this one is in the back. It could be in either place. This single term over here has to get distributed to all three terms inside the parentheses. And this is a distributive property. Does anybody remember the full name for the distributive property? It's a distributive property of something, and it keeps going. Anybody? I thought maybe you wouldn't remember.
Multiplication over addition or subtraction?
That's it. Distributive property of multiplication over, you see how these are going over the top of an addition sign and a subtraction sign. It's the only time we ever use it, over addition or subtraction. So when we multiply it into this first one, the number parts multiply together, -4. There's 3 x's altogether. Or we can think of we added the exponents on the x's. And then we multiplied, negative times negative is positive. The numbers multiply together, 6. And then there's 2x. So x squared, y squared. And then with this last one, it's still going to be a fraction. Positive times negative is negative. You make this over 1. Multiply the tops together. 4 thirds x y squared. Like this. So what we've done is gotten rid of the parentheses. It's still big and messy, but there's no more parentheses. All right, a little feedback on number 10, please. And that's it for the practice quiz. And thank you all for the support you gave me on Wednesday. I really appreciated that. And you have some things coming up. Today, the Chapter 4 test review was due, and what opened up was the answers for the test review. So you still need to upload for Wednesday the test review with errors corrected. Also, Wednesday we have our exam. The exam covers Chapter 4, which is all this stuff with all these letters, negative exponents, and all this kind of stuff that you saw in this practice quiz. You know, multiplying, adding, and negative exponents, and scientific notation. And also it has the application problems. And all right, so that's coming up on Wednesday. And so questions on homework or on anything, could be on test reviews or.
Don't we have two homework sets to do?
Yes, And on Wednesday, you'll be turning in 4.5 and 4.6. Yep. Because that's also included in the test.
Okay, thank you.
You're welcome. Thanks for the reminder. Okay, the special products, no specific questions on those problems. All right, let's go then to 3.1 and 3.2. 3.1 is to getting used to the coordinate plane, and 3.2 is graphing linear equations. All right, and we're going to start out with this problem, and this is data from 2018, and there's a little table here. Years of education. Now, 13 years of education is actually getting a high school degree, because you have kindergarten and then grades 1 through 12. So 13 years of education, the average salary is $38,000. Now with 10 years of education, the average salary in 2018 in the United States was $26,000 per year. And I put little parentheses in there to kind of make that maybe a little, if you're used to being paid by the hour instead of per year, salary per year, you multiply your hourly rate times 2. Now why do we multiply our hourly rate times 2 and then add 1,000? So $13 per hour turns out to be $26,000 per year. Well, it turns out that's really easy computation. Just multiply your hourly rate by 2 and stick the word 1,000 after it. And that's how many thousands of dollars you make per year, and translate back and forth. The reason why it's 2,000 is because we tend to work 40 hours. Let me do this with a little bit more space. We tend to work 40 hours per week times. Now there's 52 weeks in a year, but suppose you take 2 weeks off. 50 weeks per year. Now, units cancel just like numbers do. One in the denominator, one in the numerator, whether it's plural or single doesn't matter. And then 4 times 5 is 20, and then 2 zeros add on to that. And the units are hours per year. If you're working full-time, you work approximately 2,000 hours per year. So, if you're making $13 per hour, just multiply that by 2 and add the word 1,000, and your salary is $26,000 per year. It's nice to have those conversion rates as you move from jobs that are paid by the hour to salary jobs that are paid by the year. All right. And so then people that have an associate's degree tend to make on average 41,000, bachelor's degree 59, master's 70,000. So that's the basic information. Suppose we're asked to make a graph out of this. It turns out, it's always the saying, a picture is worth 1,000 words. We're much better at interpreting visual information than almost any other type of information. In fact, the way your brain processes, when you are processing intense visual information, 2/3 of your brain power goes to processing visual information. We have 5 senses, and you might tend to think that, equally important. No, about I think it's close to half of all the apparatus in your brain is there for processing visual information. It's way more visually oriented than any other sense, smell or touch and all that kind of stuff. And so it's no wonder that pictures do so much for us. All right, so what do? How do we make a graph out of information like this? Years of education and salary. Well, it turns out that in math, historically, there was no way. People could never visualize this kind of information and make graphs out of it until there's this guy, Rene Descartes, came along. And he said, hey, when you want to compare two things like this, you just put one of them on a horizontal axis. And the one that we put on the horizontal axis is the one that we tend to think of as the input. So if you look at this, we think of years of education as kind of the input, and that determines the output, what your average salary is going to be. So the input, we usually put the input first on the left side of the table. And we usually think of what's on the right side as the output. Our brains process it easier that way. If we had this table the other way around, salary first, years of education in the second column, we could still use it, but we tend to have an easier time when the thing that determines what the other one is, the input variable, we also call this the independent. Independent variable, the one on the left, and we tend to think of this one as the dependent variable, the one on the right. Now variables mean we can vary them. We can do what ifs. What if I stopped at 14 years of education? Then what's what's an average salary I might be able to expect? Okay, and then and then we say that you have all kinds of choices on picking whichever input you want. You can play what if games. What if I do 19 years? So that's independent. But this one, you don't have any choice on it. Once you've chosen your independent variable, there's just one answer. It depends on what you chose. If the input is 19, the output is 70. The input is 13, the output is 38. All right, so we put our independent variable on the horizontal axis. So that's years of education. And then on the vertical axis, we're going to put our dependent variable. So years of education. And then salary. And then we can't use the same number scales because these only go up to 20. Well, this has got to go up to 70. So if I went by fives, I could get up to 20, but I wouldn't be able to get up to 70. So you're allowed to change the scales to whatever you want. So I might make these. So this just needs to go. Highest value is 19, so we'll go up to 20, maybe by fives. And then the salary has got to go up to 70. So if I'm going to go up to 70, I got to have smaller units, and I'll go by like tens. this salary in thousands of dollars. Okay, and then we're going to place dots for each one of these points. 10 years of education, 26,000 in salary. 13 years would be about a little more than halfway, and it would become 38,000 is their average salary. 14 is 41,000. 16 goes up to 59,000. And then 19 we go up to 70,000. So we can see as you get more years of education, you make more money on average with this. And this is getting used to, is what we have here in the title, the coordinate plane. X, Y coordinate axis. And before Descartes, there was geometry, and then there was all the other math, and they never mixed together. Descartes was the one who kind of blended the math together and said, hey, we can get equations and all this kind of stuff, we can get them into graphs as well. You just make these two axes, a horizontal and a vertical, and he kind of took different branches of math and just kind of pulled them all together. And I think he was around the 1300s, somewhere in there. All right, any questions on this? All right, let's go to the next one. And this time, you make a graph from scratch. The year and the number of smartphone users in the United States in millions. So you see it went from 65 million smartphone users in 2010 all the way to 270 million smartphone users in 2020. Huge explosion. Put this information on a graph, make it visual. So I'm going to give you a couple minutes. Okay, let me do a quick check-in on groups. Is there anybody here in group 1 today? So actually, to do this, right, you have to go in Discord, go to your group number, and type in hi, group leader, make sure that the spokesman for the day knows who they are. And I'll give you just a second for that. All right, back group 1, anybody here? All right, group 2, I had you move over into group 3. So group 3, how many here?
Currently, it is me and another.
2 of you.
Yes. Actually, now it's just 3.
No, 3. Okay. And group 4, how many of you there?
There's 3 of us.
3 of you. And group 5, how many? Okay.
There's 2 of us.
2 of you? Okay. 4 and 5. All right. So, if any questions are coming up as you are making your graph, like, what do I do on this? You can type them into your group chat. Let me give you about 1 more minute, and I'm going to put up this graph. I'm getting a little bit of feedback noise, so check to see if you're muted. Alright, let me check over here. Wendy, I think I need you to mute. Great. Okay, I'm going to put this information in the XY grid. So here is the year, number of smartphone users in millions. And this, now what we can also do is we don't have to start at 0. This kind of will show that, we're skipping a whole bunch of numbers. And we're going to go from 2010 to 2020. And I'll go by 2s. 2012, 14, 16, 18, 20. You can put tiny little hashes if you want for the ones in between. And then we're going to go to 270. Probably I'm going to go to like by 50s maybe. And if I have like 6 of them, I can go up to 300. So it'll be 50 million. So on. Okay, and then I'll make in the year 2010 there were 65 million. 2012 is 120. 2014, 170. 2016, 210. 2018, 260. 2020, 270. Now you can see the need for why I'd probably want to use, as time goes on, a grid like this that's all set up, that's nice and uniform and has it could be a lot more precise with it. Right now, we're just getting kind of a feel for this. But we can kind of see that this is kind of going up like on a straight line, like, whoa. And maybe it'll plane off now. We don't know. All right, we are at a break time, so we are going to start again. At 1:34 p.m. And does anybody need to speak with me individually before I take my break? All right, see you in a bit. Okay, let's start back up again. And, all right, quadrants. In any XY grid like this, we call the quadrants, this one is quadrant 1. And then we rotate like this. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Now, the reason why we start in quadrant 1 over here on the upper right, well, it's pretty clear. Like over here, a lot of the times, all the data is positive. And there are really 4 quadrants here. 1, 2, 3, 4. 4 quadrants here. 1, 2, 3, 4. But we were only in quadrant 1. Since that's the most often used, that's where we start. Now, if we had positive numbers, see, now notice the x's. We also often call this the x-axis and the y-axis. Don't have to call them x and y, but that's their most common names. You see, everything in quadrant 1 has a positive x-coordinate and a positive y-coordinate because you go right instead of left, and you go up instead of down. To get in quadrant 2, you have to have a negative first coordinate and a positive second coordinate. Every single point over here will have, you got to go to the left, and then you got to go up. And every point in quadrant 3 is left and down, so it's negative, negative. And in quadrant 4, you go positive x-coordinate and then negative y-coordinate. And then place these points into an XY grid. Now I can do it right onto my screen. You all will be looking probably for an XY grid. You can draw one on your on a blank sheet of paper, but it's kind of nice to use one. If you've got your textbook, you might look on page 249, number 34. There's an empty grid there, and that's not an assigned problem. And you can put all these points down on that grid. Now when you put these points down, I want you to put the number of it right next to it. So put a dot, and then right next to it put 10. And then another dot, put 11, and so on. So we'll do these 8 problems, and we'll give you a minute, quick minute, to just place them all here. And again, it looks like, oh, this will be super easy, but it's really easy to get something wrong on this. That's why it's really important you do this ahead of me. Okay, 30 seconds more. Okay, so the first one. 1, negative 5 means go 1 to the right, 5 down. You don't put a dot here and a dot here, it's just 1 for the whole thing. So, common student mistakes are put dots like on both places. And then this was problem number 10. And then negative 1, 1 to the left, 5 up is up here. That's problem 11. Negative 1, negative 5. That's problem 12. So this is, remember I said in quadrant 3 down here, you're going to be, both coordinates are going to be negative, and we see that right here. And 13, 2 to the right, 1/2 up. $16, 5 to the left, negative 1.5 down. Come on. There we go, and it's 16. And then 17 is 3, 0. Now I want you to notice it. 3, 0. The y coordinate was 0. When the y coordinate is 0, you sit on the x-axis. And then number 18, negative 2, 0. Now this one, the y coordinate was 0 again, and we're on the x-axis. And then 19, 0 over 5 up is right here. And that's number 19. And this one, the x-coordinate is 0, and we're sitting on the y-axis. So it's the opposite axis. When the y is 0, you're sitting on the x-axis. When the x is 0, you're sitting on the y-axis. Now, we can think of the y-coordinate every time as the height of the point. So, number 10, 1, negative 5, right here. Its height is negative 5. 11, negative 1, 5. The height of that point is 5. So we take this second coordinate and we think of it as the height of each point. All right, and now we're kind of starting to see, if we use that thinking, why when the y coordinate is 0, you're sitting on the y-axis. You have a height above the y-axis, above the x-axis of 0. When your height is 0, then you're sitting on the x-axis. In a similar way, we can think of the x-coordinate as how much we moved away from the y-axis, how much we moved left or right. And so when we haven't moved away from the y-axis, 0 left or right, but only moved 5 up, that's when we're sitting on the y-axis. Alright. Now, a nice simple problem. Well, the graph will be so simple. Do number 5. Solve and graph 3x plus 1 equals 13. And I'm going to give you a minute because the graph part's going to seem a little crazy. But I'm going to give you a minute, and I want you to work on your own for a moment, and then I'm going to have you enter your answer with your group. So type in your answer, but don't hit enter yet, into your group chat. And go ahead, hit enter, and talk about especially what it means for this graph. What in the world, how would you graph this? Solve and graph. Okay, let me ask group 4, what'd you get for solve and graph?
We got x equals 4, and then our best guess would be to do it as like 4 along the x-axis and then 0 on the y-axis.
Ah, I like the way you're looking at that. There's two ways you might be thinking of the graph. If you thought of just the number line, the x-axis, and that's all, there was no y-axis, then you'd go 0, 1, 2, 3, 4, and you just place a dot right here. But if you were thinking of this in an xy coordinate system, you could look at it like this. Now, when you think of it in an xy coordinate system, we're going to see that it means something really different over here. And then to graph this is going to be, we said x equals 4. It'll turn out, in an xy coordinate system, you don't have to really understand y yet. But let me just explain. It'll turn out to be a vertical line at x equals 4. But there's two ways to look at it. Whether you look at it as this, or if your context is an xy coordinate system. Now, the context would have to be conveyed to you. If they said, oh, there's only the letter x and there's no such thing as a y variable in this situation, then this graph, the number line, would be all you need. If they told you, oh, this is part of an xy coordinate system and the y is missing, then it's going to turn out to be this. Right. So the main thing that we're focusing on now is probably, it was this. And if you graph, solve a normal equation, graph it, you would just get a single dot on the number line. Right. Now, let's go to this one. Solve and graph y equals 2x plus 3. In this problem, the directions don't make sense here. For one thing, the equation is already solved for y. Because when there's more than one letter in it, you can solve for one letter or you could solve for the other letter. And it doesn't mean you get the number like y equals 4 or something like this. You just get y alone on one side. Okay? So when all of a sudden, see this one, there was just one letter x in the equation. We could solve and graph. When there's two letters, x and y, then we start to have this problem. Equation is already solved for y. When there are two variables in one equation, the equation represents a relationship between the two variables. So it's all about relationships now, instead of just solve this equation. For instance, x represents the number of hours a bike is rented. and y is the cost of renting a bike. Now, like I've had visitors to Santa Fe, and I want to take them mountain biking. So we go to a bike store, and this might be the situation. It costs $3 plus $2 per hour to rent a mountain bike. And then you get to play what-if games with the variables. So we get to make a table of values. What if, and I'll say, like, what if I put 1 in for my x? Means I'm going to rent the bike for 1 hour. And then I can do 2, 3, and 4 hours. Alright, so your task now is to fill in the y for this situation. It costs $3 to rent the mountain bike, and then $2 per hour. Fill in the rest of that table, and then do that individually. But now it's hard to put in a table into your group chat, but you can just put in the points. For instance, you could say, you know, if you get a number for this one, suppose you get 17 for this, you could say 1 comma 17. When the x is 1, the y is 17. Or you could put x is 1, y is 17. Now 17 isn't the right answer, but those are a couple different ways you can put your answers in for your group chat. And let me give you a minute to get these values. Enter your answers into your group chat, discuss them briefly. Okay, group 4, what do you have for the values of y?
We've got
Did I say group 4?
Yeah.
Alright, sorry, I just picked on you. I meant group 5. Group 5, what do you got?
I think the person in my group left. I'm not sure, but so it costs $3 and then $2 per hour. So y would equal 2 plus 3, so 5 for number 1.
Good.
And then 7, 9, 11.
Good. Alright, so this has to do with our what if game, that before I even decide to rent, I might look into my wallet and say, oh, you know, I only have $9, so we want to rent it for 3 hours. But it's nice to do this what if game first so that I don't get in trouble and take it for more hours than I can afford. So now notice this equation up here looks pretty abstract. Y equals 2x plus 3. But it can represent something really concrete like this. When there's 2 letters in one equation, it's a relationship between the 2 variables. And so things like solve the equation would have a different meaning. Just get 1 letter alone on one side. Okay, so let's go to number 7. If I have 2x plus y equals 7, well, that becomes Well, like for instance, I could subtract 2x from both sides. And then it becomes y equals negative 2x plus 7. Alright, so this is again a relationship between an input variable and an output variable. So now it says to complete the table. But we've got a problem there. There's no numbers already in the table. I started you out this table with 1, 2, 3, and 4. What do we do if there's no numbers in the table at all? Anybody have an idea? What we're going to do is make up numbers. But where should we make up numbers? Should I make up a y value or should I make up an x value? Well, let me show you how easy it'll be if I make up an x value. I'll start by putting a 0 in for x. Plug in the 0. 0 times negative 2 is 0 plus 7, and it spits out a y of 7. But if I started with a y value, it's going to be harder. Suppose I started with a y of, let's say, 3. Then I'm going to have to write down this equation. 3, because I got to put that 3 in for this y right here. Equals negative 2x plus 7. It's going to take me a little while to figure out what the x is. Wow, when I plugged in an x value, it kind of just spit out a y value right away. But when I plug in a y value, it takes me a lot of work to get the x value. So I'm going to have to subtract 7. Divide both sides by negative 2. And get x plus 2. All that work to get this value here. It was much harder when I started with a y value. Why was it much harder? Well, this equation is solved for y. So if you plug in a number for your x, let's put in 1 for the x. All you have to do is, it's like a recipe. Multiply that x by negative 2, and that becomes negative 2, plus 7, it spits out the y, 5. Plug in a 3. I don't have to write an equation, I don't have to solve an equation. Just plug it in, it's a recipe. Negative 6, when I multiply it, plus 7 is 1. So, we prefer equations for an equation solved for y. And then you plug in random values for x and find y each time. So that can tell you about the relationship. Now, in the previous example, we gave a context. Number of hours a bike is rented, the cost. It's a relationship between these, and you play what-if games. But one of the things about math is you can take the equation completely out of context. So we don't even know what the x and the y represented. But it's still a relationship between these two variables. And the relationship is looking like this. Okay. And we get a table of values that is starting to show, well, this is the what if games. If the x is 0, the y is 7. If the x is 2, the y is 3, etc. All right. Now, if we were continuing on with this, we could make this table go on forever. We could just keep going like this. And once you kind of get them into a pattern, when x is 4, you're going to get negative 8 plus 7, you're going to get 1. You're going to get negative 1. And we plug in 5, you get negative 10 plus 7, which is negative 3, and so on. But you can get an infinite number of entries into this table. You could pick x to be any number you want. Right, so part B says there are actually an infinite number of solutions to the equation y equals negative 2x plus 7. Each solution is an ordered pair. List some ordered pairs. All right, so let's do that. Some ordered pairs. All right, well, let's take the first row. 0, 7. Now that's a solution to this equation. It means when x is 0, the y is 7. And you can see that when you plug 0 in for x, and if you're trying to figure out what the y is, it would 0 out this thing, and the y would be 7. But this ordered pair is a solution. And we can just go right down the list. 2, 3, that's a solution. 1, 5, that's a solution. 3, 1, etc. And there's an infinite number of solutions. Normally, this is a real big change in thinking. Up to this point, a solution was something like this one, x equals 4. And you can tell, you plug it in, you get 12 plus 1 is 13. But when there's two variables in one equation, it's not a single solution anymore. It's a relationship between these two variables. And whenever x is something, the y is going to be something else. Okay. All right. Let's go to part C. When x and y are in the same equation, and both are raised to the first power only. Now we noticed these are raised to the first power. This was y to the first, x to the first. And the graph of all the solutions, if we put all these points on a graph, there's an infinite number of them, they'll line up in a straight line. So it asks you to place the above points on a graph. So let's do that. Let's place these points on a graph. And let me get this just right. There we go. Before I start plotting points on my graph, I want to look at my x numbers. I only have to go up to 3 because there's 0, 2, 1, 3. My y numbers, the biggest number is 7. Alright, so I'm going to make my scale so I can go up to 7. Make my x's. I can spread them apart a little more if I want. Even more than this, because remember I didn't need my x numbers to go more than 3 if I was just going to graph these 4 points. Alright, now I'm going to make dots at each one of these. 0, 7. Now when I make little dots, my thing complains. So I'm going to make little x's. Okay. So 0 over 7 up. 2 over 3 up. 1 over 5 up. 3 over 1 up. What am I noticing? Oh my gosh, these are all lining up on the same line. And we even have a couple more points. 4 over negative 1 would be down here. And 5, negative 3 would be down here somewhere. So we can see that it appears that they all line up on the straight line. Okay. And the straight line thing could be really handy for somebody to visualize, like, this cost of a bike. You know, look, going this many hours is going to cost this much money. All right. Any questions so far? All right. So now I'm going to do some problems that are similar to the homework problems so that you're not confused when you do the homework. So, number 8. For the following equations, tell which of the given ordered pairs are solutions. Let me give you a minute with this. See if you can figure out what the directions are asking you to do. And enter your answer to this into your group chat. Discuss it briefly in your group. Group 3, what do you got for us?
It would seem that 0, 0, negative 3, and 12 are solutions to the equation, according to one of the members.
Okay, but 2, 4 is not a solution, huh?
2, 4 is not a solution? No. And another member just came up with the same answer.
Same, okay. Let's check out 2, 4. If we plug in 2 for the x, you're going to get negative 8. And if you plug in 4 for the y, you're going to get 4. And does 4 equal negative 8? The answer is no. And if that's the case, then this is not a solution. But if you plug in 0 and 0 for your x and y, you're going to get 0 equals 0. That is a solution. If you plug in negative 3 for your x, you're going to get negative 4 times negative 3. So first of all, the left-hand side y becomes 12. And on the right-hand side becomes negative 4 times negative 3. And that does check So those are the solutions.
Mm.
And that one's not, because when we plug it in, it doesn't lead to a true statement. Solutions lead to true statements. If it was not a solution, like 2, 4, plugging it in leads to a false statement. 4 and negative 8 are not equal. Alright, now, notice also, this had more than one solution. And a solution looks strange now. It has 2 numbers in it. It's called an ordered pair. 0, 0 is a solution to this equation, and negative 3, 12 is a solution to this. How many solutions does this equation have? Does anybody know? Anybody? There is an infinite number of solutions. Whatever value you pick for x, just multiply it by negative 4 and that'll tell you what the y is. So if you want x to be 10, the y will be negative 40. X to be 100, y is negative 400. You can keep making x as big or small as you like. You can make x fractions. You can do anything you want. That x will determine another y, an infinite number of solutions. Yeah. Any questions before we move on? Okay, let's go to number 9. For the following equation, complete the given ordered pairs and use results to graph the solution set for the equation. So let me give you a minute with number 9. Okay, let me go to group 4. What do you have for this?
So we've got, for the first one, it's 0, 3. The next one is 2, 1. And let me see, I just gotten to the last one. That would be 4. 4, negative 1.
And like, how did you get this 3? 0, 3.
Oh, since 0 plus 3 equals 3.
Great. You're thinking of 2 numbers and when I add them together, I get 3. Okay. I think that's the way I would do it too. Let me just show one other way. Some people do it like this though. They solve it for y. And then when x is 0, they plug it in here, and then it spits out the y. When x is 2, it spits out the 1. When x is 4, 3 minus 4, it spits out the negative 1. Okay? And then we take each of these 3 points, and we put them on this graph. So 0, 3, and 2, 1, and 4. Negative 1. Alright, so these points, 0, 3 is up here, 2, 1 is here, 4, negative 1 is here, and I connect these to graph the solution set. Now this has to do, remember the very first practice quiz question of the day was, how many points are there on a line? Infinite number of points. And instead of thinking of a line in the usual way, we think of a line as a whole bunch of dots that just happen to be lining up next to each other. Every single one of these dots is a solution of this equation. If x is 1/2, the y will be 2.5. And we'd get, we'd fill in all these dots. And now we think of this line in a different way. It's a whole bunch of dots that happen to be next to each other. And every single one of these dots, if you find its x-coordinate and its y-coordinate, that'll make this a true equation. These are all the solutions of this. And now, when we get to graphing equations with 2 letters in it, that's the most efficient way to show all the solutions. Because you'd have to write an infinite number of points if you're going to do it this way. Or if you were going to make an xy table, 0, 2, 4, the y turns out to be what? 3, 1, -1. You still could go infinitely long on your table. So these little arrow marks at the end just show you that here's the solutions, and it's much more efficient to write them down with a graph than any other way. Alright, so the homework is these 2 sections, 3.1 and 3.2. And you've got an exam coming up the next time that we meet. So if you choose to, that's a reasonable course of action, as you could just be getting ready for the exam. And you could hold off on doing the 3.1 and the 3.2. That is going to be due next week on Monday. Next week on Wednesday there's no school because it's the day before Thanksgiving, and the school has decided that's a holiday, no classes on that day. Alright, any questions or comments? Alright, the next time we have class, we'll have an exam. We'll cover some material first, then we'll do the exam. So it'll be a short class on Wednesday.
One quick question. It says here that the homework is not 3.1 or 3.2, but 4.5 and 4.6.
That's
for this week, right?
That's what you're going to be turning in on Wednesday. 4.5, those were already assigned last week.
Okay.
So you turn them in on Thursday. And 3.1, 3.2 are assigned today, but they're not going to be turned in until a week from today.
Okay.
Okay?
Alright, that sounds good. I was a bit confused there.
Alright. Glad you clarified. Anybody else? Alright, let me stop the video.